what I want to talk about today, I think, is kind of fun and relevant. It's called hypothesis testing, okay? And this is, really important in the real world, right? So you are trying to decide, okay, I've got the control group and I've got the group that I'm giving this experimental drug to, right? And how do I tell if the drug works, right? How can I tell whether the results I'm getting from the drug are just by chance or whether they're indicative of a real effect, right? Those kinds of things are really important, right? How do we tell whether something is working or not? Or how do we tell whether or not we are in, this situation, like, normal climate, and this situation, which is climate change? How do I know which of these two distributions I'm in, right? And so again, this is just a kind of a little one lecture introduction to this bigger concept that you could actually spend some time talking about in a higher level class, like one that would be called like detection estimation, okay? So, many kind of real world situations involve, we observe a set of data, and again, the setup here basically is that we assume that all the data we observe is coming from the same distribution, IID, independent and identically distributed. So we have a bunch of samples, say we have n of them, and then what we want to use these samples for is to test some sort of hypothesis. So, for example, these are kind of like just examples you can imagine mapping all sorts of real applications onto. So one simple thing is, this coin is fair, or this die is fair, or this process is uniform, right? Or we could say something like, this manufacturing process sorry for my bad penmanship, produces a better, whatever, battery than our old process. Right? You go through the effort of changing your assembly line and you crank out a bunch of widgets and you want to know, okay, is this process better than the old one, right? Or you want to know kind of, whether or not this signal has a different distribution than this other one. Right? So something where you're trying to tell, sorry, let's try and prop this up a little bit. Something where you're trying to tell, are these two things the same or are they different, right? And so you can take a whole lot of concepts, real world applications and map them onto kind of one of these kinds of problems, okay? So let's start with the simplest thing, which is called significance testing, okay? So the idea here is that we have, basically we're trying to tell, I have a kind of a hypothesis or a distribution that characterizes like what is normal, okay? And I'm able to characterize this normal stuff. And then I ask myself, can I reject the hypothesis that I'm normal? We all know I'm not normal, right? So here's the idea. We have a hypothesis called the null hypothesis, okay? H0, that we want to either accept that it's true or reject that it's false. Or reject as false. Okay, so for example, let's suppose that our hypothesis is that a coin that I'm flipping is a fair coin, okay? And so the idea here is that I know what the normal situation is, right? The fair coin means that P equals 1/2 for this Bernoulli trial, right? Now, if it's not fair, it could be not fair in a large number of different ways, right? So I'm not trying to characterize the alternative hypothesis. I'm just saying, okay, am I fair or am I not fair, okay? And so now I observe a bunch of coin flips, right? So I observe a collection of IID Bernoulli random variables or coin flips where, again, 1 is success and 0 is failure, right? And then let's let S, which is going to be the sum of the heads, this is basically like the number of heads. And so, you know, say I flip the coin 100 times. Now, if this sum is close to 50, well, then I can be pretty sure that the coin is fair, right? But I know there's some randomness in the process, right? So I don't expect to get exactly 50. I expect to get like maybe 48, maybe 53. So I can kind of say, well, 50, you know, somewhere around 50 is good. But if I got like 23, that would probably be likely to be very unlikely to have resulted from the coin being fair, right? And so the idea here is that I put a kind of a, well, let me talk some more, and then I'll make it clear. So something like this, you know, S close to 50 means it's probably fair. You know, S equals, you know, 23 or 78 probably is not fair, right? But can we be a little bit more precise about this? Kind of where do I draw the line between fair and unfair, okay? So what we want is something a little bit more mathematical. We want a region R so that if my sum of these n variables, I guess I can make it a little n like this. If the sum of these variables is within this region, then I kind of reject the null hypothesis. And if the sum is outside of that region, I accept the null hypothesis. And this is what's called a decision rule, right? Tells me kind of what to do. So to determine this region, I have to think about the ways in which my decision could be wrong, right? How could I get things wrong? And you kind of started to think about this a little bit, in a sense, in the homework, right? Because we were talking about probabilities of error, right? So there are two kinds of ways that I can be wrong in my decision rule. And again, if you've ever done any sort of you know, table type analysis of data, you maybe have heard these things before, right? So one is called the type 1 error. Basically, we rejected H0 when H0 was true, okay? And type 2 error is that we accepted the hypothesis H0 when H0 was false. Okay? So these things are both, you know, these things could both be bad in different ways, right? So as we'll talk about in a minute, you know, suppose that the hypothesis is that the patient is healthy, right? So if I say, okay, hey, type 1 error, the patient is not healthy, even though they are healthy in real life, right? That might mean that I have to send the patient off to do some sort of a burdensome biopsy, right? Some sort of painful thing that I could have avoided because they were actually healthy in the first place, right? So that's bad. Type 2 error is like, okay, I say that the patient is healthy when they're actually sick, right? And that has also a lot of bad implications, right? That patient goes on living their life and suddenly they realize 5 years later that, oh, I was really sick all this time, right? So these are both kind of real world implications for errors. And we're going to talk later in the lecture about kind of how I can trade these errors off, or how I can assign kind of costs or risks to how important I think each of these errors is, okay? But this is kind of where we're at for the moment. So let me stop and ask any questions so far. All right. This is someone's expensive, like, computer pen thing. Okay, so now, like I said, the setup here is that I know what the null hypothesis is, right? I know kind of what normal is. I've seen lots of examples of normal, and I can build the distribution of x based on h0, okay? So we assume that under h0, we know the PDF of the observations. Right? That is to say, we know the conditional PDF of x given that I'm in state h0. Okay? And so if that's what I've got, I can quantify this type 1 error, okay? Because I say, okay, I know what would happen if h1 was true. Let's think about how these type 1 errors could occur. So, if alpha is the type 1 error, what does that mean? Well, the region R is the place where I reject the null hypothesis, right? So what I'm going to do is I'm going to integrate the probability that I'm in that region R given that I'm in the null hypothesis, so given that I'm in H0, right? So I'm saying I integrate over R this conditional PDF, right? That's alpha. Okay? Now, if H0 is false, we can't really do anything at the moment, right? Because we don't really have any information about what the distribution is like for X in the false case, right? Healthy people are healthy, kind of in the same way, but maybe there are lots of different kinds of illnesses you could have. I don't know how to quantify what that H1 is all the time. We'll talk about that in the second part of the lecture, is what happens when I can do a better job of characterizing H1. But let's, for the moment, just assume that all we can do is talk about the type 1 error. So we can't really say much about the type 2 error yet. All right, so that's coming up. So kind of what we're going to do for our significance test is, as the user, I am going to set a value of alpha, right? I'm going to say, I can tolerate a type 1 error of this much, no more, right? What is the corresponding region then in that case, okay? So this alpha is what we call the significance level. Of the test that we're going to, or the rule that we decide on. And we will determine R, the region, based on a desired value of alpha. And so, again, let's think about what we'll expect to happen, right? So a smaller alpha, what does that mean? It means that we want to be very careful not to reject the null hypothesis, right? So we're going to be biased on the side of accepting the hypothesis, So if alpha is really small, I'm going to accept that hypothesis a lot, right? And so that kind of means that, a smaller alpha leads to kind of a more conservative range of values for accepting H0. kind of that means I'm more likely to accept H0 to avoid, you know, what we're going to later call false alarms or type 1 error, type 1 mistakes. Okay. And so if you remember from, I don't know whether it was I think it was the 2 lectures ago, we were talking about confidence intervals, right? Remember we went back to all those tables of Q functions and so on. This alpha is the same as the alpha that we talked about over there, right? Where we're talking about kind of like the alpha, you know, confidence interval. And so let's go back to my coin flipping example and be a little bit more mathematical about how we could solve that problem, right? So here, H0 is the hypothesis that the coin is fair, which means that P equals 1/2, okay? And let's say that I flip the coin 100 times. This is equal to the number of heads in 100 flips, okay? And now the problem I'm going to solve is determine the significance test at a level of 5%, okay? What that means is that my alpha is going to be equal to 0.05, okay? So let's kind of think about what we're going to set up here, right? So kind of what I expect is that 100 coin flips are going to basically be enough coin flips to get me to a Gaussian approximation of the sum or the mean, right? Remember, because as I add up a whole bunch of the same random variable, eventually everything becomes Gaussian. That's what the central limit theorem is saying. So kind of what I expect to happen is that I'm going to have kind of a bell curve centered around 50, and then in this region, I'm going to say that this is the place where I would accept the hypothesis is true, and this is the region where I would reject the hypothesis. Okay? Okay, so the region that I have is going to be something like, you know, integers outside of this range 50 plus or minus some number, right? So the question is, how wide should I make this band, okay? And so now let's kind of solve the problem. So here my alpha is 5%, 0.05, and this is the probability that I reject the null hypothesis when H0 is true. Mathematically, that's like saying, what's the probability that this sum is not in this region, 50 plus or minus C, given that H0 is true? And then that's like saying the probability that my sum is further away than 50 by the number C. And then here, what I'm going to do is I'm going to divide everything through by 100. So I'm going to say the probability that the average value minus 1/2 is greater than C over 100. Right? So this is the sum. This is the mean. And now I'm going to compare this to the central limit theorem. Which was basically saying that the probability that I am further than this number, z sigma over square root of n from the mean, is approximately 2 times q of z, right? That's like saying, what's the probability that if this is my mean and this is outside of the mean, right, it's 2 times this tail, right, which is the q function. So now I kind of make stuff equal to each other. This is like saying, okay, my alpha has to be equal to 2q of z. Solve for z, right? That's like saying that z, q of z, has to equal 0.025. And then I didn't bring my q table with me today, but I can look this up in the table and find out, okay, the corresponding z is 1.96, okay, from the table, which I don't have in front of me, but you have to trust me because I'm a professional. So that tells me that I know what z is, and now I kind of reverse engineer to say, okay, I'm trying to now equate this thing over here with this thing over here. Now, what do I know? So z is 1.96. Sigma is the sigma that comes from the binomial distribution. I can get that from the table. This is basically from table for the binomial distribution. And then I divide by square root of 100. This has to equal c over 100. And then I solve for everything. And I guess that what I get is c equals 10, as it turns out. Pretty clean. So that means that my region then is basically outside of 50 plus or minus 10, right? So this is kind of the usual pathway that you would take, right, to solving these kinds of problems. I tell you alpha, you look up the corresponding z value in the table, so you know what you should put on the right-hand side, and then based on that z, the number of things you have, the sigma for the random variable, you kind of back out what should the interval size be. Okay, so questions about this example? Okay, so this is the situation that you are in when you can characterize very carefully the null hypothesis, but you can't really say anything about the alternative hypothesis, right? You know, not H0. And that happens a lot when, you know, you don't know what the unknown, I guess that's what unknown means, right? You don't know what this variable could look like in the bad case, right? But there are some situations where you may be able to get information about, okay, I'm in one of two states of nature, and I'm able to characterize both of those hypotheses fairly well, right? In that case, I can do even better than what I just talked about here for significance testing, right? So that's what's called hypothesis testing. Am I in one place or another? So this is what I would call simple hypothesis testing. So the setup is similar. You know, if we can characterize the alternative hypothesis, call that H1, then we can perform what's called a hypothesis test. Where, for example, you know, maybe H0, my null hypothesis is that the target is absent, and I have some distribution of what the observation should look like in that case. And then I have a hypothesis that the target is present. And I have a distribution of what X should look like in that case, right? So suppose this is like a kind of a radar application where I know what the sky should be, I know how I sense the sky when it's clear, and I know how I should sense the sky when there's a plane there, right? And I have a lot of data that I can use to build these two hypotheses, right? Now in this case, if I kind of go back to the ways that things can go wrong, right? So if I go back to my type 1 and type 2 errors, right? So let's recall that this here was only in terms of when all I knew was H1, right? Now that I have two hypotheses that I can both kind of characterize well, I can actually give these things different names. So in this case, the type 1 and type 2 errors have special names. So the type 1 error, same idea as before, is I decide H1 when H0 is true. And again, this is like saying that I decide the patient has the disease when they don't actually have the disease, right? And this is called a false alarm. Okay? And type 2 is the opposite. I decide H0 when H1 is true. Right? That's when I say the patient is healthy when they're actually sick. That's called a miss, or a missed detection. Okay? And so you may remember that we actually introduced this kind of idea maybe a few lectures ago, right? Maybe around Thanksgiving time. We were talking about, like, is this a salmon or is this a tuna, right? This is actually the same problem that we've already talked about. So we already kind of talked about this before, but I'm just going to kind of revisit it right now. And just like in the last lecture, there are different ways of trading off how these errors are weighed, okay? And so, for example, last time we talked about, so we previously talked about what was called the maximum likelihood test. And for a two-hypothesis case like this, the way that works is basically I say, you know, if the PDF at x given h1 is bigger than it is at h0, then I should choose h1. And if the PDF at h1 is bigger than it is at h0 is bigger than it is at h1, then I should choose h0, right? So kind of graphically, it's like saying I have two PDFs, right? This is like the h0 case, and this is like the h1 case. And all I do is I choose, okay, if this is my value of x, I compare, maybe it's better to say here, I compare what is the PDF at h0, what is the PDF of h1. I take whichever one is bigger, and I choose that hypothesis, right? So you can kind of see there's like a crossover point here where they're equal, and on this side, I would decide h1, and on this side, I would decide h0. Okay? Whichever hypothesis has the bigger PDF. And this is sometimes written in a more compact way, more concisely. Sometimes you may see this written as I look at the ratio of this number to this number. This is called the likelihood ratio. And then I ask, is this bigger or less than 1? If it's bigger than 1, I choose h1, and if it's less than 1, I choose h0, right? So this is like a kind of a compact way to write this kind of if this, then do that statement, right? You just kind of say, okay, if it's bigger than 1, I choose h1. If it's less than 1, I choose h0. Okay. So comments or questions about this? Okay. One thing I'm not going to talk about in any detail, but let me just say, there's also just in passing, I'll just say, there's something called the Neyman-Pearson test, or the Neyman-Pearson, test. which you can read about if you're more interested. And here you'll notice that this test, the maximum likelihood test, doesn't involve these type 1 and type 2 errors that I introduced earlier, right? It just says take whichever one's bigger. The Neyman-Pearson test tries to bring these things together. It basically says I minimize the miss or the type 2 probability given the given a specified value of the false alarm probability. So that's something that is a little bit more explicit about, I tell you the false alarm probability alpha, say, and then you find for me the test that minimizes the miss probability, okay? It turns out that in this case, you get a likelihood ratio test that looks the same way, except that, let me just kind of draw, in this case, this number, will depend on the alpha that I specify, right? So I'm not going to talk any more about this Neyman-Pearson test other than this, right? Because the thing I want to talk about is the Bayesian test, right? So after this homework, you should kind of have it drilled into your heads now that, there's the maximum likelihood version of the world, and there's the maximum a posteriori or Bayesian version of the world. And the Bayesian version is the one where you also take into account the prior probabilities of things happening, right? So to kind of go back to the medical example, we want to have these priors to say, okay, again, patient is sick or healthy, right? I may have, big concerns about declaring a healthy patient as sick or a sick patient as healthy, but I may also know, for example, that this disease that the patient is being tested for is extremely rare, for example, right? So I shouldn't be so quick to declare the patient is sick if their tests come back positive, because I know that a priori, it's very, very, very unusual for that patient to be sick in the first place, right? So we want to take the prior probabilities of H0 and H1 into account when making our decision, okay? And I feel like I already gave you a homework that was kind of along that line, but let me just kind of come back to it now that you know a little bit more. So the Bayesian world, the Bayesian, or what's called the maximum a posteriori hypothesis test, is the following. Okay, so the setup is we have the likelihoods, same setup as before, what the observation should look like under each of the two hypotheses, okay? And the prior probabilities which I'm going to call P of H0 and P of H1, right? These are kind of like my a priori understanding. And on top of that, I'm going to assign some costs depending on the possible outcomes of the test, right? So I'm going to say C00 is the cost of saying that H0 is true and deciding that H0 is true, right? This is like saying that I have properly accepted the null hypothesis. Then I have the situation where H0 is true, but I decided H1, right? This is what we called a type 1 error or a false alarm. Then I have C10, which is H1 is true, but I decided H0. That's what we called a type 2 error or a miss. And then I have C11 is going to be H1 is true, and I decide H1 was true. Right? So C00 and C11 are the good cases, and C01 and C10 are the bad cases, right? So this allows us to decide on different costs depending on the circumstances, right? So for example, let's suppose that we're in kind of like a airport security screening checkpoint, something that is near and dear to my heart because of my research, right? So in that case, we may say, okay, there's no cost to making the right decision, right? So the cost of making the right decision here is 0, right? I pay nothing for that, right? I may say that, you know, false alarms, right? This is saying that, you know, the security screener goes off on my bag and someone has to take it out and go through it, right? So that maybe I assign some small cost, like 2, right? Because, you know, it costs me something to go through someone's bag and clear a false alarm. But then here, this C10, letting a bag go through that has a bomb in it, but no one catches it, could have a very high cost, like 1,000, right? So I basically am assigning a trade-off between how much I value false alarms and how much I value misses. And what I want to do overall is minimize the expected total cost, right? So this lets me kind of trade off these things explicitly. So we want a decision rule that minimizes the expected value of the cost, right? And the cost is basically, again, like the law of total probability, right? It's like saying, okay, I am in the first case, right? So I say, okay, I have this cost times the probability that I choose H0 given that H0 is true times the probability that H0 is true in the first place, right? And then I have the cost of choosing H1 given that H0 is true plus the cost going the other way. And then the final cost, right? So these are the 4 ways that I could make choices and pay costs weighted by the possibility of each of those things happening, okay? And so we can show, I mean, I'm not going to show it right now because it's a little bit tedious, but I mean, what it all comes down to, I think I showed this actually before Thanksgiving when we first started talking about this, is that the decision rule that minimizes this average cost or I guess the expected cost turns out to be this. Same form as before, it's a likelihood ratio where if this is greater than some value, I choose H1, and if it's less than some value, I choose H0, and the value is made up of all of these pieces. Okay. So this is kind of an all-in-one thing. It includes the priors, it includes the costs. And so I could say, you know, suppose I'm in some sort of setup where I don't really have any trade-off between the false alarms and the misses, right? So for example, this will simplify if I say, okay, you get 0 cost for making a right decision, and you get, you know, a unit penalty for making the wrong decision. Then what I have is that this simplifies to it actually, well, I'm going to write it like this, but then what's on the right-hand side just becomes the ratio of the priors. And actually, if I were to multiply these things around, this would be the same thing as saying, you know, the same as the maximum a posteriori rule, which is to say that I choose the larger of probability of H0 given X and the probability of H1 given X. Right? That's kind of what a Bayesian would say, is that, you know, I don't want to choose the bigger likelihood, I want to choose the bigger a posteriori probability, given the data and given the underlying likelihoods of these things happening. Okay. So let me pause and ask, any questions here? So let me do a little example, okay? So this is kind of the thing that you might do if you were in a communications theory class. So let's suppose we have a binary communication system. Okay. What this means is that the system is either transmitting a +1 or a -1 across the channel. Okay. And the thing that you get on the other side, the received signal, as is typical, you know, gets noised up with some sort of a probabilistic thing that's added to my original bit. So basically, the received signal is the transmitted bit plus some sort of Gaussian noise. And now I realize that maybe I haven't actually introduced this notation before. This is basically notation that says the n means normal or Gaussian distribution. And then the 0 says mean 0, and the 1 means sigma squared 1, right? This is kind of like a standard way of writing the Gaussian parameters in this nice little parentheses thing, okay? And so what I want to do is I want to send bits across the channel, and I want to be able to decide on their side, okay, was this a +1 or was it a -1, right? Now, if there's not that much noise, then the +1 and the -1 look like little Gaussian distributions out on their own, but if the noise is large, then those distributions could overlap, and if I get a bit that's like 0, or if I get a signal that's like 0, it's like, well, is this a +1 or is it a -1, right? So I have to make that decision, I have to draw the line somewhere, right? So let's say that we transmit the same bit n times, and what we get on the other side is these random samples x1 through xn, which in theory are all just kind of like random messing up of the same bit, right? So now what we want to do is we want to determine the maximum a posteriori receiver or decision rule to recover, was I +1 or was I -1, okay? And so let's just write it out, okay? So my hypothesis H0, let's suppose, is that I transmitted n -1 bits, and my hypothesis H1 is that I transmitted n +1 bits, okay? So now I can build the two distributions that correspond to the null hypothesis and the alternate hypothesis, right? So my distribution under H0 is basically, you know, it's n Gaussian. So it's saying, what's the probability this is what I saw given H0? Since everything is IID, that's like saying I have the probability like this, the probability like this, and so on. So really, that's like saying I have n times the Gaussian or the Gaussian distribution times itself n times. So I have 1 minus 1 over square root 2 pi to the n, and then I have sigma equals 0, so there's no sigma to worry about. And then I have e to the minus 1/2, and then I have the sum of the bits I got, and the mean in the -1 case is minus 1 squared, or plus 1 squared, right? And under the alternate hypothesis, I have the same 1 over square root 2 pi to the n, e to the minus 1/2, and here the mean is plus 1. Okay? And now the Bayesian, the maximum likelihood thing, or I'm sorry, the maximum a posteriori thing to do would be to compute the likelihood ratio, right? So the likelihood ratio is I take this PDF over this PDF. And so the 1 over square root 2 pi's drop out. And what I get is in the top, I have xi minus 1 squared. And then I have a whole bunch of xi plus 1 squareds. That's the ratio. And if I work this out, I'm going to have all the x squared parts are going to drop out, all the minus 1, all the plus or minus 1 stuff is going to drop out. I'm just going to have the sum of 4xi, I'm sorry, minus 4xi, as it turns out. Or a different way of saying this is e to the 2 times this sum. Okay? Or making it even easier, it's e to the 2 times the sum of these n random variables. Okay? And so my likelihood ratio test is going to basically be saying I take e to the 2 times this sum and I compare it to some threshold, some sort of threshold. And that threshold is, again, if I go back to my kind of general setup, the threshold is all this junk over here, right? Now, what I can do, what you're going to see a lot in communication systems and so on, is to make life easier by taking the log of both sides, okay? That's called the log likelihood, oddly enough. So we can equivalently think of the test as operating on the log, the natural log of the likelihood, to get rid of all the e to the whatevers, right? So that means that what I have is the sum on this side, 2 times the sum, and then I have my decision rule. And then what's over on this side, I basically have the log of this stuff that comes from the priors and the stuff that comes from the costs. And if I were to kind of make this a little bit easier, let's suppose that I have, you know, breaking up stuff with the rules of logs, right? I'm just going to say I've got this minus this, and then I have plus some other junk, which is the log of the costs and stuff. So let's suppose that I make life even easier, and I say that, you know, if we use the usual costs, by which I mean no penalty for right choice and the same penalty for the wrong choice, whatever, that stuff will cancel out. Then that means that the likelihood ratio is basically saying I compare the sum to this number here. getting rid of all that stuff. And then I could say, well, okay, so if the hypotheses initially are equally probable, right? So if I know that I'm just putting an equal amount of +1s and -1s through the channel, then this just becomes 0 on this side, right? So, and that's the same thing as the maximum likelihood test, actually. So if the inputs are equally probable, that is to say that the probability of being in either case is 1/2, then the result is just saying I choose, if the sum is positive, then I choose H1. If the sum is negative, I choose H0, right? That's kind of like saying that, again, I expect that in the, that was a pretty crappy drawing, but something like this, right? So this is kind of like saying that, if the two distributions are crossing over like this, then it makes kind of sense that my decision point would be here at 0. It says basically if I add up all the bits I got, if it's net positive, I assume that I transmitted a 1. If it's net negative, I assume I transmitted a -1, right? But, if the prior probabilities are different, so if the prior of having a -1, for example, was a lot bigger than the probability of having a 1 bit, that would basically be saying like -1 is more likely. And what would that mean? That would basically be like saying that log of this thing would be bigger than log of this thing. And that would move the decision boundary over to the right. So that even though the two decision boundaries would be, this is like a crappy drawing from the very beginning. Let's throw that away. So it would be more like this, to say, okay, here's my one distribution, here's my other distribution, but given that I think that this is so much more likely, my decision boundary could be like over here, right? So I'd have to be really positive in the sense of, Sn would need to be a lot bigger than 0 to accept the possibility of transmitting 1, right? So that's kind of the idea, is that I'm trading off the priors, right? Okay, so questions or comments about this? And actually, just as a side note, if I want to be a little bit more specific for those of you that are interested, so this is like saying here, this is like saying I add up all the numbers. A different way of thinking about this is to say, I could also think about looking at the mean, right? Divide everything through by n. I equals 1 to n of the xi's, and I would choose 1 over 2n times this ratio. Another thing to notice, if I think about things in terms of the mean, is that as n goes to infinity, then what's going to happen is that this average will be the same on this side, but what will happen here is this will go to 0, so this threshold goes back to 0, regardless of the ratios of the priors, right? One way to think about why that is to say that, after I see tons and tons and tons of data, I'm willing to accept my eyes. I'm willing to accept all this evidence as opposed to this prior that came from somewhere else, right? So kind of, in some sense, the decision rule is a balance between the evidence that I see with my own eyes and my prior probabilities. And in the beginning, the prior probabilities outweigh the evidence, but as time goes on, in this case, the evidence kind of outweighs whatever ratio those priors may be, right? So again, these kinds of topics are kind of interesting to think about, but I'm not going to go into these in a lot of detail in this class because this is just like the, appetizer for a deeper discussion in another class. So let me pause and ask, any questions about this? All right, last thing I want to say is that so we kind of talked about, we're doing this kind of in a order, right? First thing was I knew the null hypothesis, but I didn't know anything about the alternative, right? Then I said, okay, I know everything about the null hypothesis, and I know everything about the alternative hypothesis, which is not necessarily that realistic either, right? So there's kind of a middle ground, which is called composite hypothesis testing, where you still know the null hypothesis, but you are a little bit more uncertain about the other one, right? So this is called composite hypotheses. And again, this is just a palette, not a palette cleanser, a mousse-bouche. So here, this is like saying we're testing a null hypothesis against a family of alternate hypotheses. So what I mean by that, for example, is to say, maybe the null hypothesis is that the mean of the distribution is 0, okay? And maybe the alternative hypothesis is that the mean of the distribution is greater than 0, okay? So in this case, I'm not specifying exactly what I think the second mean is. I'm just saying, are you in the 0 case or are you in some positive case? The mean could be 5 or the mean could be 5,000, right? So in this case, the H1 world is a little bit more diffuse than telling you exactly what the alternative is, right? So in these kind of situations, we do what's called measuring the power of a test. And what that means kind of is to say, we can specify a type 1 error, alpha, right? This is like saying, I can know about alpha because that only depends on the known distribution of H0, right? And then I can create a curve, which would be something like 1 minus something like this. This is like saying the probability of rejecting H0 when the true parameter in H1 is theta, right? So here, this is kind of like saying this is the type 2 error. And then theta, for example, theta could be the parameter that I'm trying to talk about, right? And my test is parameterized by this unknown thing. And so what you kind of do is you look at, okay, we would want this error to be pretty small when this theta is approximately, whatever I was saying it was for the null hypothesis. And I want it to be bigger as theta gets far from theta 0. So don't worry about this part too much. I just want to kind of introduce the concept that, there's more to say about this whole concept of hypothesis testing depending on how much you're able to characterize about the null and the alternative, right? And you can even have composite hypotheses on both sides. You could say, okay, one hypothesis is that the mean is negative, the other is that the mean is positive. Both of those things collect together a whole bunch of distributions, right? Or you might say something like, okay, the null hypothesis is that the distribution is Gaussian with 0 mean. And the other hypothesis is that the distribution is some sort of exponential, parameterized by that lambda, right? And then you have to kind of look at your test over all the possible values of lambda. So anyway, I don't want to talk too much about this, but just to say that if you're interested in this kind of thing, then you should definitely look into this course called Detection and Estimation Theory, which is kind of a fun course. So those of you that are like a coterminal degree student, you might look into that kind of course. Okay, so comments or questions? All right, that's it. See you on Monday for the last lecture.